we just discussed belief propagation, which again is an extremely efficient algorithm for doing probabilistic inference in tree-structured probabilistic graphical models. Again, very efficient, time linear in the number of variables n. So the next algorithm of our two inference algorithms I told you we're going to discuss is called variable elimination. So this is going to be more expensive in general. In fact, much more expensive, can be exponential in the number of variables, as we're going to talk about in just a minute in the worst case. But it has the advantage of applying to any structure of probabilistic graphical model. So to motivate variable elimination as an algorithm, let's give an example. So we're going to use as an example the following kind of a toy probabilistic graphical model. This has to do with a student in a course and variables pertaining to that student, like how intelligent the student is and the coherence with which the course is taught and its difficulty, which then influences the student's grade. The student also has an SAT score, that's a standardized test, and the quality of the letter of recommendation they get from the professor, whether or not they get a job, and whether or not they live a happy life. Whatever, this is not too important for, we're going to use this just as an example. And we can convert this to a Markov random field. I've done that here. Notice we've added mortalization edges. There are a couple. We have, for example, grade and job are co-parents of happy, so we added that edge here. Another one is, for example, between difficulty and intelligence. We're going to be doing our inference on the Markov random field form. You'll note that we've been doing most of our inference on the Markov random field form. That's one of the reasons we defined Markov random field as a probabilistic model, even though more often in practice we end up using Bayesian networks in practice because they're sort of much more intuitive to define. But for inference, generally we want to be able to think about factors over variables in general, and the kind of potentials of a Markov random field are a better fit for that. So we can write out our joint probability over all of our variables. All we've done here is what we've done many times before, which I've just written this as a big product of all of our factors or all of our conditional probability tables for each of our variables. By the way, let's say that all of our variables are binary random variables. Let's imagine we want to do probabilistic inference on this model. So to do that, and suppose in particular we want to compute the probability of J. Now, to do that, we have to sum out all the variables we don't care about, which in this case is everything other than J. So to compute this probability, we need to get this big expression here. Now notice that this is totally intractable, very computationally expensive, because let's say each of these are binary random variables. To do this sum, we need to sum over all of the different combinations of these variables, and there are 1, 2, 3, 4, 5, 6, 7. So we have to sum over 2 to the 7 possible values. So this is going to be very expensive. We might be able to do it for this probabilistic graphical model, but for anything even a little bit bigger that we might see in practice, this is not going to work. So here's the intuition behind the variable elimination algorithm. So first thing I did here is I took this and I converted it into its respective potentials that we defined before. So again, these are just these values here. All I've done here is I've just called this psi c over c, this one as psi d c over d c, that's this one and this one respectively, and so on. So this thing we can write as just that big product that we saw on the last page. Now, what I'm doing here is I'm taking the sums and I'm pushing them inside the list. So notice I have this sum over c here. Recall that I can always take a sum and I can push it in past factors that don't involve it. Or to say it the opposite way, I can take a factor that doesn't involve c and I can pull it outside of the sum. So for example, this is a big product of things, including this potential here over j. I can take that potential, notice that it involves just j, l, and s, and I can pull it outside the sum over c. And in fact, it doesn't involve d, I, h, or g either. So in fact, I can even pull it farther. I can pull it out to there, which notice that that's exactly what I've done here. The only thing it's inside is the sums over L and S, which are in our factor here. One thing to notice is the order of the sums here matters. Mathematically, I can write the sums in any order I like. I've just chosen this specific order for now. I'll talk in just a minute about what happens if I choose a different order. So I've taken each sum and I've pushed it as far in as it'll go. So now notice I can't take this sum over c and push it any farther because both of these factors have c in them. And the same thing goes with d. I can't push it in farther because there's a factor of d in here. And likewise for I, there's a factor I here. Now notice that I could theoretically take this factor over c and I could pull it outside the factor outside of the sum over d. But because of the way I put the order of the sums, I can't take this factor outside of the sum over d without also taking it outside the sum over c. And I can't take it outside of the sum over c because it involves c. So I can't pull this out here. So that's just to show you that I've pulled factors out of sums to the greatest degree I can, given how I've ordered the sums here. Okay, so now let's see how I do my computation. Recall that if I look at the computation in this form, then I'm kind of stuck. I have to do a sum over 7 things in conjunction. But what if I do it in this way? So here's the thing we can notice. This thing here, this I can represent as a new factor, I'll call it psi star, over c and d. And then notice that c, there's this sum here. So once I take the sum over c, I end up with this new factor that we're going to call tau 1, and then this is just a factor over d. I can continue. Notice that I've taken this whole thing here and I've replaced it with tau d. And notice the critical thing here, which is that c goes away because, again, we've already taken the sum over it. Now, this thing here is a factor over 3 variables, g, I, and d. D also here. Once I take the sum, I get a factor over g and I. I can keep doing this. So I've done this for each one of our sums here. So this is the first one, it was just over d. This one over g and I. I include this here. Again, I get this multiplication over things involving s, I, and g. I sum out I get a factor over g and s. I keep doing this. Here I'm summing out h, summing out g, and then finally I sum out over my outer sums s and l. Okay, how long computationally, how much computation was required for me to do this sum once I pushed the sums inside these factors? Well, let's see how long each step took. So this step here, I had to do a calculation over all the possible values over c and d in order to take the sum here. So this step took O of 2 to the 2. I'll get rid of the big O notation just for simplicity. And in fact, let's put d here so we don't get confused. D meaning the dimension or the domain size of each variable, d squared. Here, I had to do a calculation over g, I, and d, and then ultimately I'm going to get a factor over g and I. So this took d to the 3 because there are 3 variables. This one's d to the 3, d to the 3 again. The variables are h, g, and j. Keeping going. Sorry, I lost my writing that we had before. But just to reiterate, this step, d squared, d to the 3, d to the 3 again, d to the 3 again. Notice that in this step, we have 4 variables inside our sum, h, g, j, and s. But this factor here is just over g and s. It doesn't involve h. So the textbook didn't do this, at least explicitly, but when we come to do this sum, we can pull this factor out first. So this still just involves taking producing a factor over 2 variables, which requires d to the 3 time. Notice again that our running time for each sum requires time proportional to the number of variables we get in our factor plus 1 in the exponent, d to the power of the number of variables plus 1. That's because we have to compute table entries for each one of these variables, and computing each of those table or factor entries requires a sum over the variable we're summing out. So in this case, two values, so we get a plus 1 to the exponent. In this next step, notice that we have 4 variables in our sum, L, G, J, and S. Now we can't get around incorporating this factor here. This takes time, d to the 4. Then we can keep going, d to the 3 and d squared, respectively. Okay, so we did this calculation. We calculated the distribution over j. And notice that the time we took is roughly n, in this case n is 7, times d to the 4. notice that that's quite a bit less than our naive algorithm, which again takes time d to the 7. And you can imagine that if the number of variables is much larger, we could easily have a probabilistic graphical model with hundreds or thousands of variables. Even if the dimension is 2, we might see the naive algorithm might have running time 2 to the 100, as I mentioned before. So that would be way too expensive. This algorithm, if you can jig it so that you don't end up with any large factors, and therefore each one of these steps requires, let's say, only summing over 4 variables, you can get a very fast running time. In general, the running time of this variable elimination algorithm equals O of n times d to the k plus 1, where k is the largest one of these factors we produce in the process of variable elimination. And again, if k is much less than n, this ends up being much less than d to the n, which is the running time of the naive algorithm. Okay, so that was an example to show how this would work for a particular problem. So now let's try to define this algorithm a bit more generally. I'm not going to define it completely formally. I'll leave that for the textbook. But in general, the variable elimination algorithm works as follows. The first thing we're going to do is we're going to choose an elimination order to the variables. We can choose any order to the other variables that we want, but as I'll talk about in a second, the order turns out to matter a lot. So here we've chosen this order, C, D, I, H, G, S, L, in that order. So I start with the first variable I want to eliminate, C, and I ask, give me all of the factors involving C. So notice that in my network here, this one, this one, this one, this one, this one, none of them involve C. It's just these 2 factors that involve C, so good. I can eliminate C from my problem. That is, I sum out C and I get this factor over D. So now I'm going to remove these 2 factors. By the way, at each iteration, I'm going to store my state as a big list of factors. So I start out as the list of these 1, 2, 3, 4, 5, 6, 7, 8 factors. In the first step, I want to eliminate C. I take all the factors involving C, which turn out to be these 2. I sum out C, and I get this factor. Now I end up with a list of 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7 factors. Okay, so that was iteration number 1. I just eliminated C. Next, I go to D. Again, I collect all the factors involving D. Again, notice that it's just these. So, and then I do that same step of combining them into one factor and then summing out the one I want to eliminate. So this is, I'm just explaining the same thing I just did, but now from a more algorithmic perspective. So the way this algorithm would work if you were to actually code this up, again, at each iteration, you have a big collection of factors. You pick the next variable you want to eliminate from your ordering. You collect those factors, sum out the elimination variable, and then continue. So that's the algorithm. So I told you that you can use any order to eliminate the variables that you want. But as I said, the order matters a lot. So let's give an example of that. Let's say I decide that the first variable I want to eliminate is, let's say, G. So again, we're going to do the same thing. I have my big list of sums, And to express this mathematically, the variable I want to eliminate first, I'm putting the sum over g as the innermost sum. And then I have all my potentials here. So I'm going to try to push my sum over g inside. Let's see what potentials end up inside. That is, in the first iteration, which potentials do I have to multiply together? It ends up being, let's look, this one involves g, this one, and this one. Which means that once I eliminate g, I'm going to produce a factor which is going to depend on I, D, L, H, and J. Okay, so now writing down this factor, I said in general we take time proportional to the number of things in the factor plus 1 as the exponent to the domain size, so that's d to the 1, 2, 3, 4, 5, 6. This, by the way, is only slightly lower than the time it would take to run the whole naive algorithm. So what's happened here is that I've used a bad elimination ordering. I've ended up creating this giant factor over many, many variables. Remember, to write this factor down, I need to create a factor, meaning a probability table, with 2 to the 5 entries in it. So this would be, it wouldn't just be a problem in terms of computation, it would also be a memory problem, because I actually have to put that whole table in memory. So my mistake here was eliminating a variable that's kind of very central to the network, and therefore I ended up, to eliminate that one, I had to create this factor over many variables. So we just talked about how one variable elimination in some cases can give you running time for inference that's much, much lower than you get from, for example, a naive algorithm. And again, this applies for graphs like the one we have here that is not tree structured. So this applies in general. So there are a couple of questions. The first one is, can I figure out what the best elimination ordering is for a given network? The answer turns out to be no. That turned out to be an NP-hard problem. But intuitively, the thing we want to do is we want to eliminate nodes that aren't too interconnected. So you'll notice that in our original ordering, we started by eliminating C, and then D, which is not too connected now, and then I, and then H. Notice that we're kind of coming from the outside of the graph in. And in doing so, we end up not sort of inducing associations through these factors that we create in the process of variable elimination, that we don't end up inducing dependence between too many variables that weren't dependent in the first place. Now, the second question is, for a given graph, is it even possible to do inference quickly? So it turns out that for some graphs, it's impossible. So for one thing, if I have a probabilistic graphical model that involves in it somewhere a potential over, let's say, 100 variables, well, there's no getting around the fact that I'm going to have to do some computation over that potential over 100 variables. But that's kind of obvious, because for someone to hand me that graph to begin with, they already have to hand me that potential over 100 variables, which they're probably not willing to do to begin with. But it turns out that there are even some graphs that inference is very expensive, in fact, proportional to exponential in n. So for example, 2 to the n inference cost, even if there are only potentials between, let's say, pairs of variables. So this happens in general. I'm not going to give a kind of perfect counterexample, but this happens in general when there's kind of no way to break off chunks of the network from one another. That is, there are kind of lots of interconnections between all pairs of variables. So there's nothing like this where we have some variables that are kind of off on their own in the network. So in general, I'm not going to prove this, but in general, doing inference in probabilistic graphical models is NP hard. That is, at least we think that there exists, for some networks, no way to do inference in less than exponential time. We can define the tree width of a network like this. The tree width of a network is defined as the smallest factor, the size of the smallest factor we would get from running variable elimination on that graph. And tree width is a great way to understand how easy it is or hard to do probabilistic inference in a given graph. By the way, notice that any tree-structured probabilistic graphical model I'll leave this to you to prove, but if it's tree structured, running variable elimination gives you the solution for a particular ordering, which I'll also leave you to figure out, it's not too hard, gives you a running time similar to what we get from belief propagation. It will be roughly d squared n. Might be d to the 3n. I haven't double checked that. But in any case, it's low degree polynomial in the degree and linear in the number of variables. So trees have tree width 1. Or tree width 2. There are different definitions based on if you calculate the size of the factor before or after you sum out the variable. But that's not too important. The point being that this concept of trees generalizes to things that aren't exactly trees. So if we take, as an example, let's look at a Markov model with order 2. So recall that a Markov model with order 1 is just a chain. A Markov model with order 2 has one-step hops. It's easy to see. First thing, let's think of just our Markov model with order 1. It's easy to see that that has tree width 1 or 2 if you have the 1. It's not too hard to see. I'll leave this to you to determine as well. If you use variable elimination on this second order Markov model, the biggest factor you get is of size 3, and therefore this second order Markov model has tree width of 2 or 3, depending how you do the definition. So low tree width, no matter how many variables are in our second order Markov model. So again, this is a way of generalizing this idea of trees. This, in some sense, you can think of as kind of tree-like, in the sense that it's long and skinny and doesn't have any big, long-range dependencies among variables that would make inference very challenging. Okay, so this is the definition of tree width. Again, tree width is the minimum, the size of the maximum factor you get after applying variable elimination. By the way, as I said, it's impossible to figure out what the best variable elimination ordering is, so even just figuring out what is the tree width of a given probabilistic graphical model, that's even NP-hard. But the reason this is useful in practice is, let's say I come to you and I say, I've come up with this probabilistic model that I think represents what's going on in my system, whether that's economics or biology or medicine or whatever. And I say, can you do inference for me? Well, you can look at it and, well, first thing you might do is you might just plug it into some inference algorithm. But that's kind of bad because, well, what happens if it runs too slowly? Maybe there's just something that's a little bit slow about the implementation, maybe you could improve it, or maybe there's something mathematically challenging. One thing that you can do is you can use this concept of tree width. You can look at it and ask, what's the best variable elimination ordering? And often you can figure this out just by looking at it. Again, by coming from the outside of the network in. In this case, we would want to go in this order, 1, 2, 3, 4, or backwards, either one works. And what's the biggest factor we get? And if you can see that you can do your variable elimination inference without producing a big factor, then you can say, this is a small tree width network, and I can absolutely do inference for you efficiently. It's going to be fast. By the way, I should say that the running time of inference in a model, again, we saw this already, but just to reiterate, is n times d to the k plus 1, where again, k is the tree width. So again, linear in the number of variables, exponential in the tree width. So the reason I really want to emphasize this is you'll see this talked about all the time when it comes to doing inference. We really have to restrict ourselves. If we want to do inference in a given model, which we normally do, we have to restrict ourselves to low tree width models. If the tree width is high, we get inference that's exponential in that tree width, and inference becomes very expensive.